Hey everyone, in today's video we're going to be solving the problem floor in a BST. So you're given a BST with a number of n number of nodes and your value x, and your task is to find the greatest value node of the BST which is smaller than or equal to x. So when x is smaller than the smallest node of BST, then return -1. Okay. So what the question is basically saying is that you're given a BST binary search tree like this, and you're given a value x, and you need to find the floor of it. The floor of the binary tree of x can be easily be equal to x, or the least smallest value just smaller than x. So if I have 87 over here, 87 is equal to 87, so the floor of 87 is going to be 87, right? But if I have something like 11 over here, right? If I look over here in this tree, what is the value which is just smaller than x but not equal to x? That is 9. So 9 is going to be the output for this tree. For x is equal to 11, the floor of x is going to be 9. Okay, so this is what the question is. But how are we going to solve this problem? Let me just code this out as in when I explain it. So let's do a floor equal to -1 by a default value. And what we do is we loop through the tree while root is not equal to none. Okay, very straightforward till here why we're doing all of this. Now what we do is firstly we'll check if our root dot data is greater than our x, right? If so, for example, our root dot data is 2, right? Is 2 greater than 87? So no, true is not greater than 87. And what we do is we'll just go to the right of the tree. Now when we go to the right of the tree, we'll also change our floor value equal to our root dot data value. Okay, now if our floor is equal to root dot data, we also change this to root is equal to root dot right. Root dot right, right. So we're going to go to the right of the tree now, because our data is less than our root dot data, which is 2, is less than x. We're going to go to the right of the tree. Okay, now when we go to the right of the tree, we're going to change our floor value, which is now currently equal to 2. Okay, we'll change it to that. Okay, now we'll go to 81. Okay, for 81 we'll again check, is 81 greater than, you know x? So 81 is not greater than x, right? So 81 is less than x, so again we'll go to the right of the tree. So if 81, so actually over here it should be like this, because 87 is greater than 81, right? So if 87 is great, basically in the very first case, because 87 was greater than 2, we're going to the right of the tree. Now if we go to the right of the tree, we want to find the most minimum value currently, which is going to be 2, which is less than 87, right? So we make floor equal to 2, and we go to the right of the tree, which is 81. Now again we'll check with 81. We'll see that 81 is again less than 87. So we'll change our floor equal to 81, which is the most minimum value lesser than 87. Right. Now what we'll do is we'll go to the right of the tree, we'll check with 87 now. Now 87 is equal to 87 is equal to 87. So that is going to be basically a root of the tree. Basically going to be the floor of the tree, and we'll just return that value. Okay. So this is going to be when root dot data is equal to x. Okay, but now what if there's a case like this? Let's go to the second example and see that root dot data is greater than x. Now when we have something like this, right? First case, when we have 6 and our output and our x is 11. When we have 11 is greater than 6, right? So basically our x is greater than root dot data. So we go to the right of the tree, and we change this to 6, because 6 is the most minimum value, greater lesser than most greatest value, just less than 11, right? So we change this to 6, floor equal to 6 in this case. Now we check with, now we go root dot right, which is 8. We check with 8. Now again 8 is less than 11, so we change floor to the most greatest value less than 11, which is 8. And we go to the right of the tree, and we go to 9 over here. Now when we go to 9, we see that 9 is again less than it, so we change it to the most minimum value greater than, just lesser than 11. We change it to 9. Right, now we again go to root dot right. But if there's a case something like this where root dot data is greater than x, we'll just do a root dot left in this case, where we go to the left of the tree, right? So if we go to the left of the tree, for example, if we had something like 7 as our output over here, 7 as our x over here. What we would have done is you would have checked 8 with 7. If our x would have been 7, we would have checked 8 with 7 and we'd seen that 8 is greater than x. So we'd have just moved to the left of the tree, and then we would have seen that 7 is equal to this value, root dot data. So we'd have just returned root dot data. But if we had something like 5 or something as x, we would have seen that 7 is also greater than 5. So we would have again gone to the root dot left, and we would have changed. We would have actually gone to root dot right, and we would have changed the floor dot value equal to 7 in this case, and we would have returned 7. Right. But over here in our question, when x is 11, we go to this value, we go to right, 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 we reach 9, and we say that floor is equal to root dot data, which is 9, and we go to root dot right, which is equal to none. Now, when we reach none, we come out of the loop, and in the end, we just return floor. So let's just run the code. Yeah, so the code is running, and let's submit it. Yeah, it's also getting submitted. So yeah, guys, that's all for today's video. If you like the video, do like, share, and subscribe. Do let me in the comments what kind of videos you want next on the channel. Do check out my podcast as well. We have amazing speakers coming on and speaking on different topics related to career guidance, job opportunities, etc. And until next time, guys, thanks for watching.